Hello everyone, my name is Ahmed Elag and today I will be presenting my CP319 bonus assignment, which is digital system stopwatches using T flip-flop counters. So for an overview, I designed a stopwatch that counts from 0 to 99 hours, and the idea here is that I wanted something to count seconds and minutes from 0 to 60 and hours from 0 to 99. So essentially we were looking at two modulo 60 counters and one modulo 100 counter, and they all must be synced to represent real time using hardware logic. I verified my design through Falstad Circuit Builder and EDA Playground using VHDL. So to make the design easier, we use two reusable counters, a mod 10, where it counts from 0 to 9, and when it sees a 10, sends out a signal that forces a reset, which resets the counter to 0, and when it sees a 9, it creates a high signal to trigger the change of the next counter. The modulo 6 works in the same way, but it resets on 6 and sends a carry signal on 5. Reusing these two counters over the whole circuit helped me achieve the final goal of a complete synchronous counter, and it also helped a lot with the debugging, because if I could get these two right and then just copy paste them over and over again for all my counters, that means they all run right, and for testing I wouldn't have to wait 99 hours to test it for one run. So the formats are as follows. For seconds, we have second ones, which uses a mod 10 counter, therefore resetting on 10, sending out a carry signal at 9, and runs a 1 Hz square wave clock. So it increments when the clock and the previous flip flops are high, and clock is on a rising edge. Then we have the second tens, which uses a modulo 6 counter to count from 0 to 5, resets itself on 6, sends out a carry signal at 5, and runs on a clock of the second ones carry, therefore making it only update every time the second ones goes from 9 to 0. The minutes portion runs exactly like the seconds, using a mod 10 for ones and a mod 6 for tens. But the clock of the ones uses the carry from the seconds tens, and the clock for the minute tens uses the minute ones carry, and so on. The hours portion runs the same as the previous parts, but uses two modulo 10 counters, so it can count from 0 to 99, not just 0 to 59. So this design allows me to synchronize the three parts of our counter using 6 counters as timers driven by each other. So for high level architecture, just to get a sense of the idea in an engineering sense, we will use T flip flops to make our 6 counters, and then we want to take these outputs and connect them to 6 7 segment LEDs to see our stopwatch run in real time and be able to actually use it. So as for inputs, each counter we have clock for S1, which is the second ones, and then a global reset and a counter specific reset, which are the reset 10 and reset 6s, depending on which modulo counter we're using. And then we have the S1 carry as S2 clock, S2 carry as M1 clock, M1 carry as M2 clock, M2 carry as H1 clock, and finally H1 carry as H2 clock. As for outputs, we get a total of 21 output bits, 7 from seconds, 7 from minutes, and 8 from hours, which we can then connect to our 7 segment displays or decoders and then displays and view our outputs respectively. Just like how it is shown on this drawing right here. The seconds connected to the first two LEDs with um, 8 input decoder being connected, like the 8th signal being connected to ground, so that it is always 0, and the same exact thing happens for the minutes. Hours gets connected to all 8. And then now let's move on to my low level architecture and see how I really built and designed the circuit. So the modulo 10 used for S1, M1, H1, and H2 uses 4 T flip-flops. And just for review, T flip-flops are edge triggered sequential circuits. So that means the Q value gets flipped on every rising edge of the clock it is running on. So if T is 1 and the clock is on a rising edge, if Q was 1, it'll become 0, and if Q was 0, it'll become 1. So to create a synchronous counter, I then connected our first two flip-flops, or our first flip-flop to a constant 1, which is our enable signal. Then the following 3 flip-flops to the enable signal with an AND gate to the previous Q, meaning they both must be high. This created the logic so that the second flip-flop only increments if the previous flip-flop is 1, and the third flip-flop increments if the enable first, second cues are all ones, just so it can actually work as a counter, making it a true synchronous counter, which will then be the seconds timer ones driven by a 1 hertz clock. Our reset works when a 10 is detected using AND gates for 1010, which is binary for 10, or the global reset is used, or it's high. And our carry signal works the exact same way, but for binary 1001, which is 9. So every time it sees a 9, the green circuit here, which is the AND gates, will go high, which sends a signal to the next counter, which we will see shortly. The modulo 6 works the exact same way, but uses 3 flip flops in the binary 110 for reset and the binary 101 for carry. So here we can see that the carry, basically all the green circuits here are the carries and how it carries out from an example like second ones to minute ones. So the second ones carry goes to second tens, and that is used as the clock for second tens. So every time the second ones goes from 9 to 0 or it reaches 9, then this second tens is allowed to increment itself. So it would be plus one, plus one, plus one every time this second ones hits 9. And then similarly for minute ones, it is ran by the carry of the second tens, which is also the high signal carry for second tens. And then the same way goes for the rest of the counters. The minute ones passes on to the minute tens passes on to hour ones, and then hour ones on the right here passes on to hour tens. And obviously, hour tens does not have a carry because there is nothing that we could use that for in this design yet. So the idea here is that we have the clock, and then when we get all 21 inputs, as explained previously, with a global reset, which creates our complete module. So this would be like a middle level architecture. We have the specific resets, the global reset, the clock that goes into S1, and then how everything is connected with the carries, which uses which is used as a clock for the next counter. And then we have all of our outputs on the right side here. And then finally here is our Falstad verification. I labeled them seconds at the top, minutes and hours, as well as you could see which counter is which with H2, H1, M2, M1, and S2, S1. After building, the biggest challenge was to build the S1, S2. Once I got them running right, it was basically just a copy paste procedure from there, but the only difference is it uses a different clock for each of them. And here we can see how it runs in real time. So we can see at the bottom right that as it touches exactly 1 second, we get incremented for our seconds. That's exactly what we were looking for, just to make sure that the 1 hertz clock is actually running the counter as a timer. And then increasing it shows that it just increasing the clock makes it just go faster for the sake of demo. And you can see how the second tens or S2 incremented correctly. And then here is a very fast demonstration just to make sure everything else is working. And sorry about the one panel not working on H1 here. It was just a small connection error. I ended up fixing that, and it should be in the report so you can test it out for yourself. Lastly, I went over the VHDL simulation and how exactly I implemented it in the report, but however, this is just a demo to show you here. And then the waveforms at the bottom also shows that the second ones, every time it hits 9, second tens is incremented, and then more towards the right, we can see that once we hit 5, once we finish the 5th incrementation of second tens, second ones is incremented from 0 to 1 correctly. So for challenges, the problem was implementing like a modulo 60 and a modulo 100 counter was not practical directly, because then we would need 220 flip-flops and they require large amounts of logic to detect values 60 and 100. Reset and carry logic becomes even more complex, and then it's also harder to map and almost impossible to do on Felstad, or it would be very, very time consuming. So the solution here was I split up the modulo 60 counters into a modulo 10 plus a modulo 6 counter, and then the modulo 100 counter to 2 modulo 10s. This made the design modular, cleaner, and easier to debug, as well as If one of them works, or like the modulo 6 and the modulo 10 work right, then I know I could just copy them and they will work right throughout. And then another issue here is ripple counters introduce propagation delay. So each flip flop toggles only after the previous one changes. This can cause temporary incorrect states, which are glitches in real hardware. The solution was to keep counting frequency low in simulation using clear carry chain logic and verifying rollover behavior in both Felsted and VHDL waveforms. For future improvements, I think this circuit can convert ripple counters to fully synchronous counters. So remove the propagation delay, and produce that. This would end up producing reliable like time for real hardware, and actually use it as a reliable stopwatch. And this also makes the stopwatch scalable to higher frequencies. A second idea would be to add up down timing capability, just so how we have up down counters. We can have it work as a timer and a stopwatch at the same time. And then the timer mode would be the counting down, and the stopwatch would be counting up from 0000. And then this basically would just require us adding direction control input and borrow logic for countdown, and a small FSM to switch modes. So if it was like if M equals 0, it would be a stopwatch. If M, which is mode, equals 1, it would be a timer. Lastly, maybe we could add full user interface features such as lap split time, or hold resume, or even countdown alarms, or maybe even preset hour, minute, and second inputs. Thank you very much for watching my presentation. Have a great day.